stick a goto at the beginning, and then explain to the compiler where you meant double break should land you. Okay, and then if we have conflicting pins, then overlapping equals false. And so overlapping equals false just tells it, hey, you're going to get this set here to be empty when you subtract them. So there's no point in doing any of this work here. You might as well just say do this. Now, what about the minus FB part? Well, that's a good point. Maybe I oversimplified this a little bit. If the input characters are non-overlapping, there's no interlap between this and this, then this turns out to just equal FA, right? But if the input characters do not overlap, does that necessarily mean... So this would become FA, and this would become empty set. Right, so if this and this have no intersection, then we just need FA x TA, right? So that's the first case. The intersection of the letters is empty. If the intersection of the letters is non-empty, but the intersection of the flags is empty, then this here will work out to be empty, but this is still non-empty, right? Or this, rather, is still not the same thing as FA anymore. So this is actually not correct. It's more like this. If not overlapping, as in if not this statement, which means this statement, else we are overlapping in our input character space. So the next question is, suppose we get here and we have conflicting pins. Well, we could rewrite this a different way, right? Because this is the same thing as FAXTA. Well, let me put it this way. This is the same thing as, it's still FA that, but this here could be the part where we put the intersect instead. Why? Well, this is all parallel. The only reason the order FAT, like FT is sticking is because it determines the order of the pair, but they're completely symmetrical in relationship to each other. T and F don't define anything in a special way that makes them behave differently than the other one. They have the exact same behavior towards each other. So it should be the case that this and this give me the same result. But let me do just a quick double check here. So before I was saying, alright, this is everything, every number that FA has that FB does not have. So every number that FA has that FB does not have means 4 and 5, and cross that with every letter that TA has. So all the numbers we didn't subtract out, crossed with all the letters that we originally had, gives us this rectangle here. And this part here says, given all the letters, or all the numbers that both of them have, so 1, 2, and 3, in other words, all the letters that FA had that were subtracted out, that's another way to put it, crossed with all the numbers that TA has that weren't subtracted out. So, or all the letters that TA has, right, T is the letters. All the letters that TA has that are not subtracted out. The letters that are not subtracted out are E, F, and G, right? So 4 and 5 times all of the letters, and then 1, 2, and 3, the things that did get subtracted out, but multiplied by the letters that didn't get subtracted out, right? So that's cool. And so that suggests the way of splitting up the nodes is that and that. But you could also just split up the nodes the other way around, is what I'm thinking, right? So I could say all of the numbers that A has that were not subtracted, 4 and 5, times all of the letters in A that were subtracted out, F 4 or 5 times A, B, C, D. A, B, C, D were subtracted out, and that gives us this rectangle here, union with all of the numbers that were in A, times all of the letters that were in A that were not subtracted out, right? So times that, E, F, G, H. So that gives us this as one node and this as one node, right? So we can either do this as one node and this, or this as one node and this. Does that make sense? I guess another way to put it is, here's one way to split the two nodes up, and the other way is like this. Make sense? Now, when we have a situation where either of these intersections turns out to be null, the other node, that node becomes empty, right? We're basically saying we have two nodes, but if this is null, then if this is the empty set, I should say, then this here is all we actually need, one node. If this is the empty set, that means we have conflicting pins, right? Remember, T represents I'm imagining that T is the flag support part of our system here. So, if this had the flag configurations A through H available, and this had the flag configurations A through D available, E, F, G, and H are left over. But if I drew a different picture where this also had E, F, G, and H, then all of the flags would be getting subtracted, like all of the letters would be getting subtracted out. That still wouldn't kill everything because we would still have 4 and 5 left over, but it would just be the 4 and 5 of this section here, right? So I guess another way to put this is if all of the letters are subtracted out, that doesn't mean that every instance of all the letters are subtracted out. That just means that all of the letters are subtracted out where the numbers are, intersecting, right? But in those places where this has unique numbers, nothing happens, right? Just like where it has unique letters, E, F, G, H, nothing happens to the numbers. So, it's possible still that this is a copy of the node. So let me double check that. If this is an empty set, that implies also that this here, this subtraction, does nothing. In other words, TA intersect TB is empty, therefore TA minus TB should just be equal to TA. And so the cross of this is just equal to FA cross TA, aka it's equal to the original node. So this is a situation where we can output the copy of the node again, like that. Now, finally we are in a situation where the intersection of FA and FB is not empty, and the intersection of TA and TB is not empty. So now what we need to do, we already have the intersection of the letters. That was the first thing we did. So we already know the value of our set FA intersect FB. But we don't know the value of the following sets: FA minus FB, TA intersect TB, or TA minus TB. And we need all of those sets to be represented so that we can construct our two nodes. We also need to decide which of these two ways we're going to use. So it turns out that whichever one we take, we need to do the subtraction for both, right? So we can't get away from having to do both of those subtractions. So the only question is, would we rather do this intersection or that intersection? And as I just pointed out, we've already done this intersection. So I propose we use this one, because that way we can just use the existing intersection to create this node and use the subtraction that we're going to have to construct either way to create that node, and then we don't have to do any extra work for the flags. We just do that one, right? We basically already are computing this, so we get less work for ourselves if we use this formula, basically. Now, the other thing we haven't done yet is we haven't actually made sure that the intersections were not empty. We didn't make sure that these here, FA minus FB or TA minus TB, were not empty. That might be worth doing too. So how do we know when that happens? Well, FA minus FB happens when the input intersection is exactly equal to this FA, right? If intersect if AF intersect FB equals FA, then this subtraction is empty. And if that subtraction is empty, then this node disappears, and we only need this node, right? Similarly, if TA minus TB is empty, then this node disappears and we only need this node. If they're both empty, then the whole thing is empty and we can return an empty node. So we do need to know if either of these things are empty now that we're at the point where we know we can't just copy the node. So let's do that first. I'm going to call this input subtraction is empty equals input intersection count equals in A count. So if the intersection count and the A count are equal to each other, then the subtraction of the A minus B input sets will be empty. Now, what about this? How do we do this stuff with T's, right? We've done all of the stuff we can do with characters. We still need to compute TA minus TB and TA intersect TB. Or at the very least, we don't need to compute TA intersect TB, but we would kind of like to have the ability to do that in the case where this is empty so that we can just emit one node, right? So we're not always going to do that work, but we do need to be able to do that work when we need to, right? Does that make sense? But before we can figure out if we need to do which intersection we're going to use, or if we're going to use if we're going to use only one or both, we need to find out if this is empty. We also need to be able to figure out how to subtract that in general, because one of two things is true. Either this is true, in which case this is empty, and so we're going to use this right here, because this right here will be the easiest one to create. This is just the original input times this. I mean, it's the same thing as this. These are the same thing, right? If this intersection is equal to FA. So, if that's it is true, we need to be able to do that subtraction. If it's not true, we also need to be able to do that subtraction, but we need to be able to do that subtraction to figure out if the subtraction is empty, right? So we need to start thinking about that. When is the subtraction empty? When is the subtraction this is wrong. So whenever we do a subtraction, the number of fields should be larger than it was beforehand, or at least equal to it, right? So the subtraction is empty if this equals this, right? If that minus that equals that, then this subtraction here, wait, that's not just an empty subtraction, that's an empty intersection. Right. How do we tell when the subtraction is empty? I guess the subtraction would be empty in a couple of ways. For instance, we can get an empty subtraction by just saying that, right? If they're both the exact same set, I'd definitely be empty. Furthermore, if I pin down a flag over here, that only shrinks my set. Anytime I subtract this set here, I'm going to get the empty set. So a lot of the time I'm going to get that TA minus TB is empty. Actually, a lot of the time, because I'm expecting that most of the time I'm going to be subtracting something like this. I would also get an empty set if I did this. Right? Because unlike this case here was empty set union this set. Remember? Because this is derived by first saying flag set 1xxx intersect complement flag set 1xx0, or to put complement a different way, flag set xxxx minus that, which is to say flag set 1 xxx intersect flag set 0 xxx minus flag set xx, or union flag set xxx1. And then when we perform that intersection here and distribute it over the union here and here, we get the empty set union flag set 1 xx1, right? So an intersection is applied in the following way. If we know the intersection is non-empty because we didn't get any conflicting pins, and that is what would indicate conflicting pins would be what indicates an empty intersection, right? So for a non-empty intersection, all we have to do is say none of our pin down flags overlap. So let's just glue all of the flags together. Or to put it another way, if you look right here, when I intersect this with this, it becomes empty because they like contradict each other. But this intersected with this just becomes 1xx1. They have pins in places that are they have pins in different places, and so they just become one series of pins that concatenate those two different pin things together, right? And if they ever agreed, if they both had a 1 here, then they would just output a new one that also just had a 1 when you intersected them, right? So that's all an intersection is, which means that to build the intersection is not that hard. What about a subtraction? What does a subtraction take? If we want to build a subtraction, we need to, using the formula suggested here, construct the complement of this, which is the chain of every individual bit flipped, eliminate all of the ones that are contradictory, and then intersect in the ones that it's a lot more complicated actually to build a subtraction. But like I was saying before, we have to do a subtraction in either case, right? The only time we can avoid a subtraction is when this is empty because then we can do this. So here's a question: can we use an intersection to get the answer? So there's a relationship between an intersection and a subtraction that's kind of useful. In particular, if this is empty, right, that means that FA minus FB is equal to FA. And if this is equal to FA, it means that FA minus FB is empty. And so we might be able to easily figure out if a set is empty by just saying, do these two flag pin chains turn out to be equivalent? They have the same number of flags when we intersected them as before we intersected them. Yeah. Then we could find out that these are empty, and an empty subtraction would mean we have an easier time, because that's just one set there. The only time we're really going to be hurting is when the intersection, we can easily get this TA intersect TB. When we're going to be hurting is when we need to get TA minus TB, I think, because it's neither empty nor exactly equal to TA. But let me think about it a little bit more still. I'm still not convinced that we found the best way to do a subtraction. So maybe there's a simpler algorithm that would have given me this minus this. So I have that minus that. If it was just that, I would get an empty set here. I don't know. I feel like this expansion is the most obvious way I can see how to do it. I mean, what other logic is there? Whenever we're subtracting from that, it's just easy. It's the complement rule, right? And the complement rule is for every pin we have, create a singular thing that inverts that pin and union those things together. And then if we're subtracting from something like that, what do? Well, we just have to do a pass over it that says remove the contradictions, and then a final pass that says combine this in. I don't see how else we can do it. Yeah. All right, that's gonna have to be what we do. So, let's first see if the subtraction is going to turn out to be empty by seeing what the intersection looks like. The intersection is not going to be that hard to construct. I just wish I could think of a way to use the intersection to make it easier. I didn't write down a whole lot of these intersections, right? So like the intersection, the subtraction of this and this looked like that. The intersection of the two of them, I think, would look like this. Because this is a more specified than that, right? That's my theory. Could I use that to get to this? I don't see how. It's the same information I already had. The only thing I have is that, like, I know now that that's the intersection, but that doesn't seem to be changing anything useful. I mean, now I can take that and get the complement, and I still have to intersect this. Yeah. I mean, I guess the best we could do is to basically follow this as a formula, but implement it all in line with some slightly tighter logic than it would look like, than what I would get if I like actually wrote it out as like unions and intersections in C. So that's probably what we'll do. But let's do the intersection first. So an intersection between these two flag systems, or flag set things, is oh, I don't have a flag set. Okay, so that gets us caught back up to where I left off. Okay, so how do we do a flag intersection? we just loop over each of these. First we do the transition condition flag, a flag equals a flag pins dot first, node equals a flag. For each one of these we create a transition condition flag, new flag, push it onto the arena. Push array 0, transition condition flag 1, the new flag is just a copy of the A flag. And then we push that onto the flag intersection. Now we do the same thing for B, only there's one difference, which is we don't always do the push. First, before we do the push, we have to do another loop over a flag list here. We'll call this the C flags, and these flags are the actual flag intersection flags themselves, and we're going to say is duplicate equals false if C flag equals the B flag, then is duplicate equals true, break, and then if not is duplicate, then we push the B flag onto the intersection. So that gives me a way to take any two flag sets and intersect them. So now, if the flag intersection count is equal to the A flag pins dot count, then this set is exactly the same size as this set, right? They both have the same exact set of pins because we know that every flag in A got pushed on there, and so the count was at least going to be that big, and it didn't grow, therefore this didn't push anything new on, and it's the same exact set. So the flag set is the same. I need to go back to my set algebra here. So if the intersection of TA and TB is TA, then TA minus TB is an empty set. That's the idea. If TA minus TB is an empty set, then we can just emit this. Hold on, I thought we already did that logic. They have no conflicts. Up here I determined that they have no conflicts. Up here I determined that the intersection is not empty. Here I determined that intersection is not empty. Why was I doing that? So if this intersection is empty, the point is that's an empty intersection, just return this. If that's an empty intersection, just return this. In both cases what we really mean is just return a copy of A. In this case, okay, so in this case TA intersect TB is empty. No, TA minus TB is empty. Therefore, we only need one node. I see. So if input subtraction is empty, then that means that we just need to pick one of these and use it. And the point is we can pick either one because this FA and that are the same thing. The intersection is full, aka FA equals FA intersect FB, but we still need to perform the subtraction. So we should have not done this work if we were in that situation. In other words, if the input subtraction is empty, we want to do one node right there, and otherwise go ahead with this. So I think that it will make a lot of sense to pull this out. It just looks like a lot of code, even though it's not that complicated. And that's just, I don't know, a good sign that I should pull it out and make it look as simple as it feels. Intersect pin sets. A, B, and an arena. A flag pins dot becomes A dot. B flag pins dot becomes B dot. And then we return the enter result. Transition flag condition flag pins equals flag intersection equals SMI flag set intersect flag pin set intersect pin sets, which just works by saying I need the arena, I need A pin flag pins, and I need B flag pins. It gives me back a flag intersection, and then I can find out if flag subtraction is empty. And if I finally get here and neither of them are empty, then I have to actually do out a flag subtraction and return a result based on that. But if I can avoid it, I am trying to, because it just means less nodes. And although this is all meant to be easy to maintain code, an empty node would actually be an error. So I feel like this is not just an optimization, it actually is necessary. And so while I'm having to do this anyway, I might as well be cleaning it up. Now there might have been simpler ways. I might have been able to do the subtraction first and always do it, and then just not emit extra nodes or something, but I don't know. I don't know. This is certainly intricate. So the input subtraction is empty, means that this was empty and all we need is this. FA intersect FB, or FA, which are going to be equal, times TA minus T. I still need TA minus TB, huh? I might have problem then. I think I just need to do the intersection at this point, no matter what. No, there's one case where I don't need to do the intersection, right? Or the subtraction. If that subtraction turns out to be empty, so if I do this intersection and it turns out to be equal to TA, then I don't need this subtraction and I can avoid it. So that's what the optimization here is this is the case where you don't need to do the TA minus TB. Which, to be honest, is the expected case. I feel like that is going to happen more often than anything else. But for here, what I'm going to need is I'm going to need this chain linked list of nodes that are generated from subtracting TA from TB and assigning each of them FA as their input. So that's gonna have to go up here because it's getting too hot in the middle of that procedure. So that's definitely going to need an arena, and it's going to need to know the input that it's giving to everything, as well as the input count. And then it's going to need the two flag sets. So transition condition flag transition condition flag condition. Where's the flag pin type? Flag pin pins actually means no. Flag pin pins means flag pin set. There we go. Okay. So I want two flag pin sets, A minus B, and there we go. So I want to construct one of these things. I give it an arena, I give it the input of A, and the in A count, and then I give it the A flag pins and the B flag pins. And that should give me the right thing if I do the right thing over here. Let me see. I want to do that in a minute. Looks like I'm going to turn this into 3 hours, doesn't it? Okay. So that's the subtraction. That minus that, and the multiplication times that constructs a chain, because it's not really obvious that I can just do the subtraction in isolation, because the ability to chain things is actually owned at the node level, not at the flag set level, so I can't make a chain of flag sets and stick it into a single node. I actually have to generate a bunch of nodes, with each one being one of the outputs of that subtraction algorithm. Okay, what about the case where that is empty? In that case, I can get away with just doing this, right? So I need FA minus FB, which I'm going to need in either of these two cases now, because either I'm going to do both this and this, or I'm going to do just this. But doing just this just means I need the subtraction, which I don't actually have yet, but I can easily get that. So what we need to do is do the subtraction code for the inputs. Input subtracted equals push an array onto the arena of U16s. Wait, why don't I just reuse the input space? That's going to be the same thing, right? So I'm going to call this subtract input subtraction equals input intersections, and then I'm going to say I32 input subtraction count equals 0, and then this does a lot like what this did, to loop over all that stuff, but this time I am going to do something a little different. I'm going to say B32 is subtracted equals false, is subtracted equals true. If it is not subtracted, then we do it right there, right? And then instead of input interactions or intersections, we call this input subtraction, there, there, and there. And so that gives us an input subtraction array, and we can use the input subtraction array to build up either of these two cases, or both of them, is what we're actually going to do. Just at runtime it will be one or the other, but right now it is both. Okay, so there's our f minus a minus fb. Now if our flag subtraction turned out to be empty, then we don't actually have to do this case, we're just going to use this one node. And so for that situation, we're in really good shape. All we need to do is manually construct a single node and stick it into a list. There's nothing else complicated about it. Transition condition node, new node equals push an array onto our arena, give me one new node, and then go and show me that struct. Thank you. So the new node flag pins can just be a copy. Do I have a flag pin copier? I'm not sure that I have a way to copy flag pins. So I guess the point is the subtraction is empty, so we are going to be... I do have a way to copy subtract. That's right. Node copy. Right? So what I actually need here is flag pin set SMI flag pin set copy. This looks like this. Arena. Looks like that. Oops. Result first, result last, new flag. Getting these off the set now. And then this can just be SMI flag pin set copy arena flag pins. Okay, so now we can just do flag pin set copy on the arena, grab A's flag pins like that. And then what else do we want to do on the new node? The new node's inputs and input count can be derived. There's no point in keeping that ordered like that. Can be derived right up here. So we have input subtraction and input subtraction count. We then take the whole thing and we go like that. Whatever. Okay, so that right there is a good case. We have so far the following cases. The inputs are completely non-overlapping, in which case we copy the node. The pins are completely contradictory, in which case we copy the node. The input subtraction is empty, in which case we have to do a flag subtraction operation, which is a bit costly. So if the input subtraction is empty, that means that the thing we're subtracting away is contains all the inputs that the thing we started from had, and nothing is left. It's a possibility. It won't happen all the time, but it can happen, I think. Pretty sure. Although in that case, I would expect that the final result will pretty much always be that we have like one or maybe no flags, and therefore an empty list, or a list with one element still. But you know, this is a slightly costly case, even if it's still going to produce a reasonable result. Now we have the final case. This is the case that is not a reasonable result and is costly, so that the whole thing is bad. But luckily this only happens under the very unusual circumstance where there is the intersection between both the flag set and the input set are both non-empty but also non-full. That is, the subtractions are also non-empty. This is going to happen exceedingly rarely, I think. It'd be a fairly complex state machine to have to manually construct to get this to happen in the real world, although you could easily just sit down and do it, no trouble, if you wanted to expose this code path. But I want to make sure I try to handle it correctly, and then we will put this to the test a little bit, maybe off screen though, I don't know. I should at least do the right thing in this case, right? So how do you do this one? Well, we're going to have to do the subtraction, and the subtraction is going to work on the FA intersect stuff here, so that we don't have to do this intersect. Or did we already do that intersect? Well, either way, I don't want to use this intersect because this has more likely to be complicated than this. The intersection never simplifies the flag field, so I'm going to use that flag field, not that one. And then combine that with this, because intersecting inputs does simplify it. Intersecting flags complicates the computation. So keeping the result of the simple outcome is better. So we're introducing two nodes now. Well, two major nodes, but this one here is a subtraction of two flag sets, so it could easily be in any number of nodes. But there will be one from this and then any number of these. And how do we put that together? Well, we're going to need to start with result equals blah 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 blah, as in result equals this thing, where the input needs to be... Oh, I trampled over the intersection memory. I can't do that. I do need to push a separate copy on here. That way, when it comes time to call this, I can pass it the input intersection and the input intersection count, right? And then I want to pass it those two flag pins, and great. So that gives me this portion. Then I just need to union that on. How do I union that on? Well, I'm going to construct by hand another node and push it on manually. So the another node I need is going to have its inputs defined by FA minus FB, so the subtraction and the subtraction count, FA minus FB, and the original flag set. Yeah. So just like in this case, we need this thing. Oh, interesting. So another way I could look at this is like this, I guess. My bad. So I accidentally treated that like a doubly linked list with 0 ends when it's not what that is. So I just need to put the last equal to this guy's first, set the last forward, and then increment, right? Condition dot inputs. Okay, so that's the entirety of the subtract implementation. I still need an intersect implementation, and then I still need to rewrite all the code that came after that I never rewrote when I was trying to derive the new way that these conditions are structured, because the conditions are so much more complicated now. So yeah, there's more to do. But this just became essentially a 3-episode block that I got knocked off, and that we implemented the subtract method and generalized the condition set system so that it will be able to actually represent the full scope of things that can happen once we start optimizing. So, I mean, we got through the hardest part, I think. We still need to implement a condition set intersect, which I'll start in the next episode, and then we need to do all this work, which will probably take an episode after that. So this is starting to become like a real thing, and you can see how it actually goes. But that was the point. So I hope that you've been enjoying the series, and I'll see you guys in the next video.